All right, so let's look at a state again. And now what we could do is, instead of just predicting how many variables you need, let's look at how these variables are related. So I can plot P, V, and T on a 3D plot. And this is for some substance called substance X or whatever. And if I want to know what state I have at any one point, I can figure it out from this plot. And as you can see, it's fairly hard to use. I mean, in this particular cross section, you could probably find some things, but it's not a very intuitive thing that one can use. And so what we do instead is we take 2D projections of this plot. And the one that you've probably seen in general chemistry is when I take a cross section of that with P and T specifically, and I'm looking at the phase diagram there. So that corresponds obviously to this, to P versus T. So I'm looking at that cross section there, and what I could see. This is a great introductory phase diagram, and that's why they use it a lot in middle school, high school, and introductory chemistry courses. And that's because it's not very quantitative. It just kind of tells you where things are. So if I told you a specific temperature and pressure, you could then predict to me, tell me what you think, what the phase of that substance would be, which is very useful. What you could see, again, to remind you from previous courses, what you see on this diagram are lines of equilibrium, and the line that corresponds to from this pinch point, triple point, to say point C, this line corresponds to that equilibrium between the liquid and the gas. And that means that if you lie directly on this line, both liquid and gas will coexist. So that corresponds to, for example, boiling water. When you're boiling water, you have both the vapor and the liquid and the coexisting in the pot, and that's going to be at about 100 degrees Celsius at 1 atm. And there are other equilibrium lines. You have here the solid liquid equilibrium, and you have here the solid vapor equilibrium. So going back to that Gibbs phase diagram, Gibbs phase rule, this is when the number of components would be 2. On these lines, it's 2. Outside of these lines, it will be 1. And there's the pinch point here, that's known as the triple point. That's what we were discussing before, where all 3 can coexist. That's what the number of components will be, 3. The other thing to notice here is that there are transitions, and these are their names, and you probably know them from previous classes. The one thing you probably did not discuss, and we will use to some degree in this class, is the critical point. Okay, and so the critical point defines a point where the liquid phase stops existing. Okay, and basically, the liquid and the gas have indistinguishable properties. And we call that sort of a phase, sort of a regime for that substance. We call that a supercritical fluid. Okay, so it's got like a hybrid kind of properties between liquid and gas, and it lies beyond the critical point. And so the temperature that corresponds to the critical point is known as the critical temperature, and the pressure is the critical pressure. Okay, and that's really all we can kind of use this for. This is not typically used quantitatively, so we're not going to use this much in this class. What we're going to do is, instead of taking a PT cross section, we're going to look at a PV or a TV. They both would look similar. And this will be a PV diagram. And so the dark pink dome with the dark pink dotted lines, that's what is used in your textbook. I added the light pink lines as well to show you the complete phase diagram with all the phases. But we will really focus on this dark pink dome. But let me kind of show you what this is. What's going on here. The dotted lines are corresponding to constant temperature, because I'm not really plotting temperature here, I'm plotting pressure versus volume. And as you can see, there are different regions in this diagram. I have a place where only solid exists right here. I have a place where only the vapor exists, a place where only the liquid exists. And also I have places where I have multiple phases coexisting. And we're going to really focus on this dome. So whereas in this plot, the coexisting line corresponding to one specific line, in this plot, I can resolve that into an entire dome and I have a whole area to work with, which is great. So, and I'll show you in a few minutes why that's great. What you should know about the transition zone is that when you reach, let's say, for example, for water, it's 100 degrees Celsius and 1 atm. When I heat up my liquid from 25C to 100C, the temperature will go up. So I provide heat, and in response, the system will raise its temperature, okay? And we call that sensible heat. We call that sensible heat because the heat that I am adding to the system is able to be sensed. I can measure it, I can look at the temperature rising, and therefore it's sensible. Once I reach 100 degrees Celsius, I will continue providing heat to the system, but the temperature will remain at 100 degrees Celsius and the pressure will remain at 1 atm. During this transition, any addition of energy, instead of going into a rise in temperature or a change in pressure, will go into changing the intermolecular forces between the liquid molecules so that now they're weaker and they kind of break apart and they become a gas. Okay, so we call this latent heat, and latent is an English word meaning hidden. And so the hidden heat, because we cannot sense it, the temperature will not rise, the pressure will not change. And even though you're adding heat, it looks like it's going nowhere, but it is going somewhere. It's breaking apart these intermolecular bonds. And so during that transition, what you should know, practically speaking, is that P and T remain constant. As you can see here, the dotted line corresponds to temperature. The temperature remains constant. The pressure remains constant throughout this particular transition. The volume does not. The volume will change. So as I'm going from a place where I have only liquid to a place where I have only vapor, the P and T will not change, the specific volume will, and I will eventually reach a place where I have only vapor. And then my pressure will change as I increase the heat as I go to the right. Okay, so these dotted lines here correspond to one specific temperature. If you keep the temperature fixed and all you do is play around with the pressure, you will see a change in phases. You can have a similar thing where T would be here and the V would be here, and you would have lines of constant pressure, and it would look very similar to that. And in that case, I think the pressure would then, they would go up, I think. And that at that point, when you increase the heat, all you see the temperature going up when you become a vapor. But during that transition, it will not. Okay, so that's a PV diagram. I will not show you the TV diagram because we won't really use it up. What we're going to do, instead of using these diagrams, which is a pain to kind of pull out a diagram for each substance, we will use tables instead. And we will use equations instead. But you can pull out all your information directly from a diagram if you had one. And people used to do that. So what we're going to do instead is look at the tables. But before we do that, I want to discuss specifically why I care about that dome. That dome is cool because I know that during that transition, so this is just basically me kind of copying this area and focusing on that. That dome, so over here I have a liquid, over here I have a gas, and in between here I have both a liquid and a gas. As I'm traveling across that red line where the pressure and temperature remain constant and the volume changes, I am going from a state where I have 100% liquid, and slowly as I'm heating it up, I'm going to a place where I have 100% gas. But anywhere along the red line, I'll have a mixture of the two. So whereas here's going to be more liquid and here's going to be more gas, I need to be able to calculate what % of my mixture of liquid and gas is vapor and what % of it is liquid. And so what we do to quantify that is use a quantity called the quality, and we will denote that with the letter X. And it basically means that for any random point, I call this, say here, Y, what percent liquid, what percent gas do I have here? And I will define that right here, like this, where the quality is equal to whatever point you want minus the property of the liquid, and we denote F as liquid, and the gas, the vapor, we will denote as gas, and we can calculate it this way. So YG would correspond to this point, YF would correspond to that point, and those two would be tabulated, or you can calculate them from an equation. This is what you're interested in. So if I have this one random point, am I using, do I have 50-50 liquid vapor? Do I have 25-75? Do I have whatever it is? I can use this to calculate it.